Hello guys, so recently I studied this concept and I struggled a lot to understand it, and finally I managed to understand it. So I made this video to help you understand. I hope you I hope it helps you. So uh, so there are many different implementations of this how to say of this algorithm. But today we are only going to discuss this one and this one, the most common ones discussed on the internet. Okay, so basically I think you should have implemented your p-1 algorithm by this point. If not, then you don't know the details, so you might struggle. I suggest that you implement the p-1, or you just ask ChatGPT to give you some code, the implementation, and you just run it to get a sense of it. So why did we choose this? Why do we choose these two formulas? Okay, so we choose these formulas to increase the probability that t is a multiple of p-1. So our goal is to make t a multiple of p-1, and these two formulas can help us achieve our goal. So we talk about this one first. So for any prime p, if p-1 is b-smooth, then this formula is probably a multiple of p-1, the result of this formula. I'm going to give you an example. So in this example, our p is 13 and our b is 5. So we can so our p-1 is 12. Okay, so we factor it here. So it has 2, 2, and 1, 3. And it turns out that all the prime factors are less than 5. So p-1 is 5 smooth. It's 5 smooth. Now let's apply the formula, and we get a result 60. Is 60 a multiple of p-1, which is 12? Yes, this clearly is. So in this case, we see this formula helps you produce a multiple of p-1 because we have 2 2 here, and the 2 2 is included. If you factor 60, the 2 2 is in it, and the 3 is in it. Now we discuss this one. So for any prime p, if p-1 is b smooth, then b factorial is probably, most likely a multiple of p-1. I give you an example here. So p is 13, b is 5, same as before, and the factorization is the same. So it's 5 smooth, and b factorial is 160, 120. Is 120 a multiple of 12? Yes, it's a multiple of 12. So this formula helped us obtain a multiple of p-1. Because you see here the 2 to the power of 2, this factor is contained here, is in the 4, and 3 is in the 3. So this contains all the prime factors in p-1, so it is a multiple of p-1. I hope by now you understand why these two formulas help you obtain multiples of p minus 1. But unfortunately, they don't help you obtain a multiple of p minus 1 all the time. So sometimes it doesn't work. So I'm going to give you some examples. So if you have implemented the algorithm, you must know that in the algorithm we are testing different values of b. Why are we testing this? Because, as I said before, these formulas don't guarantee that t is a multiple of p minus 1. I'm going to give you 2 examples. So before, our p is the same as the previous examples, but b is now 3. So the factorization is the same, but the LCM is 6 now. Is 6 a multiple of p minus 1? No, it's not. So in this case, LCM formula doesn't help us obtain a multiple of p minus 1. Now we are going to talk about the factorial version. The factorization is the same, but 3 factorial is only 6. Same as before, 6 is not a multiple of p minus 1. So in this case, the formula b factorial doesn't help us obtain a multiple of p minus 1. So what happens if it doesn't help us obtain this, we just increase the value of b, because as we have seen before here, when b is 5, then the result becomes a multiple of p minus 1. 60 is a multiple of 12. That's why in the algorithm we are testing different b's, incrementally increasing the b. So let me make it larger. So as you have seen, when b is equal to 3, t is not a multiple of p minus 1 in both cases. When b equals 5, t is a multiple of p minus 1 in both cases. Hence, increasing b helps us find t such that t is a multiple of p minus 1. This is a reason that we have a loop in the algorithm that tests bigger b over time. In addition, note that p minus 1 is 3 smooth. It's 3 smooth because all its prime factors are less than 3, or less than or equal to 3. So it's 3 smooth. Then we can say it's 4 smooth or 5th smooth. Why? Because we can say it's 4 smooth because all its prime factors, 2 and 3 here, are less than 4, and 2 and 3 are less than 5, so it's also 5 smooth. So we can so you can see we can increase the b as we want. So before we explained why we need these 2 formulas. We need these 2 formulas to get a multiple of p minus 1. But why do we want why do we want t to be a multiple of p minus 1? Because I'm going to explain to you. Because if t is a multiple of p minus 1, then we can write this: t equals k times p minus 1 for some integer k. If this is the case, then we have a to the t becomes a to k times p minus 1. Just substitute it, and then we arrange the how to say, the exponents. Then it becomes like this. After it becomes like this, we can apply the Fermat's-Little theorem. So Fermat-Little theorem says if p is a prime number and a is an integer such that a is not divisible by p, then we have this: a to p minus 1 equals 1 mod p. So before here we supposed that a is relatively prime to p, right? So it's certainly not divisible by p. So we can apply this formula here. Also our p is also a prime. So this is equivalently saying, a p minus 1 mod p equals to 1. So this value, a p minus 1 mod p equals 1. So we can simplify this to this. Now this becomes 1, and then 1 to the k is 1. So, and we move 1 to the left. So from here we can derive that a to the t minus 1 is a multiple of p. Is a multiple of p. So it means it equals a to the t minus 1 equals kp for some integer k. So I made a mistake here. So we have proved that if t is a multiple of p minus 1, then a to the t minus 1 is a multiple of p. Okay, this is very important. You have to like remember it. Maybe you have to you just repeat it a few times so you can remember it. So before so if t is a multiple of p minus 1, then a to the t minus 1 is a multiple of p. Why is this important? Why do we want to have such a value? If you have implemented the algorithm, you should know, because this same formula, this value is used in the GCD with n. I'm going to explain here. So why it's important? Why it's important? So now we have this value at minus 1 is a multiple of p. Then this GCD a to the t minus 1 and n is going to reveal, is going to be an r. This r is going to be p or a multiple of p. Why? Because we supposed that p is a factor of n, and p now is also a factor of this value, so it's going to be included in the r. P is going to be included in the r. So, but this part I'm not very sure. I copied it from online. But so about this, so it can be p because if these two numbers share only one prime factor, p, so then r is going to be p. But they could share like other prime factors other than p, then r is going to be a multiple of p. p because R includes other might include other other prime factors as well. I'm going to give you a detailed explanation. You can read it on your own if you want. So we are given n, and we are trying to find a factor of n. We ignore step 1. I think step 1 further confuses you. So we assume that n is a composite. We have tested that it's a composite. So, and we assume that n has a prime factor p, and such that p minus 1 is bismuth. This is our first assumption. Our the whole algorithm is based on this assumption. But our assumption can be true or can be false. Then we know that if we assume a b, for example, b is 5, because in the algorithm we guess b assume it's 5, then we apply 5 here. Then this number t, as explained before, is probably not 100%, is probably a multiple of p minus 1. This we have already discussed it in the first part. Yeah. So if t is a multiple of p minus 1, then this value a to the t minus 1 is going to be a multiple of p. Okay, if it's going to be a multiple of p, then the GCD of these two values is going to reveal a factor. It's either reveal p itself or reveal a multiple of p. As I explained in my previous page. This GP is n. Why GP is n? Because we assumed here n has a prime factor p. P is a prime factor p. So we assumed that p is a prime factor of n, then n equals GP for some integer of g. So we just substitute this. So our step 6 may fail to reveal a factor because we could have assumed the wrong value for b. We have assumed 1b. For example, before in our examples, we assumed b equals 3. Then t is not a multiple of that. Is not a multiple of p minus 1. Our p minus 1 was 12, right? So, but if it's not, if t is not a multiple of p minus 1, then this value is not a multiple of p. Then this GCD of these two values won't help you reveal a factor that contains p, because this p is not here, is not in this in this value. So if p is not here, then this GCD is not going to include p. So I hope you have understood it. Okay, so I'm going to demonstrate again the guessing game. So suppose our n is 12 and n contains a factor p such that p minus 1 is bismuth, and suppose a equals 2 and a is co-prime to p, but we don't know p. We just pray that 2 is co-prime to p. So in our algorithm, we not only guess the b, we also guess the a. In the algorithm, you see how we change a's. Yeah. So Yeah, so we assume a equals 2 and a is coprime to p, and now we only guess we guess the b. We first guess b is 3, then this number is very small, so you can see a factor of him is like 13. So it's the same as our previous examples. N equals 26. P you can see it's 13. 13, yeah, 13. So our initial guess, which is wrong, b equals 3, and if b equals 3, b the factorial is 6. 6 is not a multiple of p minus 1, which is 13 minus 1, which is 12. So 6 is not a multiple of 12. So then this 18 minus 1 doesn't include 13 in it. The 13 in it. Yeah, 13 is a prime factor. Because t is not a multiple of p minus 1. Only if t is a multiple of p minus 1, which is 12, then this value is going to include the factor 13. So it doesn't include 13. 3 doesn't include 13, right? So this GCD won't help you reveal 13 as a factor. It says, okay, it will only give you 1. But when you increase the b to 5, then t is 120. 120 is a multiple of p minus 1, which is 12. So now this value includes the factor 13 in it. So now you calculate GCD, then it revealed the prime factor 13 successfully. So through this example, you can see by increasing b, you make t a multiple of p minus 1, and this will help you reveal a factor. So I hope by now you have you already get a hang of it. But if you didn't, it doesn't matter, because you will just by watching the video a few times or find other resources. Okay, good luck with your cryptography class. Thank you for watching.